let's go ahead and look if we have a moving receiver. Okay, I'm going to come over here because my board got too busy over there. Okay, so if we have a moving receiver now, let's do the same little business where we draw what happens at different times. Okay, so if we have our source here, and it's emitting waves, and we have this is our listener right here, okay? And we'll say the distance between these crests is lambda. So now at time equals some time, other time t, I'm going to call it tr for the time between when the receiver heard the maxima. So now, if we have our receiver, our listener, is moving at some speed, vr. Okay. So in this time t, each of these waves have moved some amount. Oops, sorry. That's going to be moving a little faster than our guy, so we'll move him this way. And now he has moved here, so he's right here. So the distance that our listener moved is how fast he's moving times the time that he traveled. And let me see, it looks like this distance here is how far the wave traveled. So that's the speed of sound times the time. Okay, and it looks like between here and here, that is the total, if I drew it properly, that is the total wavelength. That's the distance between the waves. That's lambda. Yeah? Question? Okay. So we can say then, okay, so then we can say that the wavelength that was emitted is equal to this distance plus the distance that the receiver moved. Okay, so let's simplify this a little bit. Let's see, so we have TR, that's the time that the person listening, that's the time between when it heard maxima. That's just the inverse of the frequency that he's hearing. So that's just 1 over, so each term has one of those, so we're going to factor it out. Okay, the wavelength that was emitted, that's just the speed of sound divided by the frequency that was emitted. So it looks like, let's invert both of these. We have that's not going to help with the confusion. Nu over V is nu, frequency that's received, times 1 over V plus VR. So it looks to me if I solve this for the frequency that is heard, it looks like I'm going to get the frequency that was emitted by the source times the speed of sound plus the speed of the receiver over the speed of sound. Did I do that right? No? No?
Oh, you're really today.
Yeah, am I good? Okay, let's check my slides and see. Okay. Oh, we're looking for new. We are. We're looking for new. We want to know what is the frequency of the sound that the person so we have a person that's listening for the sound, but the person is running towards the source. And so he's going to hear the sound differently than somebody who's not moving. Okay? Okay. So here's the same thing we just went through. Yay, it looks like it's the exact same. Okay. So this is the frequency of the sound that the person is going to hear it. So if the source is at rest, then the frequency that the source is emitting is just nu naught. There's nothing shifted about it. But if the source is moving, what is this frequency going to be? What's the frequency of sound going to be? Huh? Ah. So let me see. It looks like if the source is moving, we've just figured out that the frequency that all stationary observers are going to hear is this. So that's the new we plug into here. So it looks like what I'm going to get, and please correct me if I make a mistake. Does that look right? Yeah, question.
Is this for the person moving and the source moving?
Yes. Very good. So this is the frequency that will be heard by the listener. And this is if the listener is moving. And this is if the source is moving. Okay? Yes, Colin.
If they're moving sort of diagonally, so they're
Yes.
not moving directly towards each other, would you take the component of the velocity that was pointing towards the other, and then use that for the calculation?
Yes. Yes, so the question was if they're not moving straight on, if they're moving at some diagonals, would you take the component that is moving directly towards each other? And yes, you would. Yes.
Is that the equation that you just wrote down? Is that if they're both moving?
Yes, this is if they're both moving. So, and let me be careful of the signs. So this equation I wrote down right here. This is the frequency that will be received. Okay, so this is assuming that the person that's listening, the receiver, is moving with some speed VR, where I've defined positive to be if they're running towards the source, okay? So if you're moving away, then this will be a negative number. And I said that this is the speed of the source, but I said that it's positive if the source is running towards the person who's listening. Now, I want to point out, it looks to me like movement of the receiver, movement of the source are not exactly treated the same. Any ideas why? Because in special relativity, we went through a lot of hoop states. It didn't really matter who was moving. It only mattered their relative motion, right? Why is it different here? Why does it matter who the heck is moving? Yeah, because there's a medium. So our premise for special relativity is there's no absolute rest frame. But here, all our sound waves, they need a medium to travel in. That means that we will know whether we are moving or not relative to whether the medium is moving relative to us. So in this case, when we had a moving source and a stationary listener, the listener knew that they were not moving because they were at rest relative to all the air molecules around them, right? But so here what we effectively did was by the source moving, we changed the wavelength of the sound. But here, now our listener is moving relative to the medium. And so what's changed here? See sound waves coming at him, but he's running toward them. So for the listener, it looks as though the sound waves are coming at him faster. So it's really two different things, which is why the equation treats whether the receiver is moving or whether the source is moving in different ways. Okay? Any questions on Doppler effect? Yeah, Marcy.
Was there an equation for just the receiver moving?
Yeah, so if just the receiver is moving, then what is the speed of the source? Then it just goes to 0. Right? And if it's just the source moving, then the receiver's speed is 0. You recover the same equation.